All right then, guys. Again, if you're just joining, I asked you to calculate the derivative of x squared times e to the x, and you can make mistakes naturally. Hopefully, some mistakes you will not make. Okay, let's see what I have here. So a lot of people wrote 2x times e to the power of x minus 1. So the fact that you wrote 2x times it, or some others wrote 2x times e to the x. Okay, let's see what is happening here. So of course, are you ready, guys? We can begin solving it. Yes. Of course, we know that the derivative of x squared is 2x, and the derivative of e to the x is e to the x. So some of you, I mean, I spoke all this thing about e to the x, and I guess the entire thing disappeared. I told you the difference, right? So there is a difference between x squared, for example, and 2 to the x. They are not the same thing. Remember how I explained that? I said that if x squared is this person, then 2, that's x squared guy, and then 2 to the x will be something like this. And to confuse between those two functions is to confuse between those two faces. And again, I wake up in the morning and again, I just, my God, you know, I don't sleep too well. This Saturday and this Sunday, I was hunting for a black cat. It's a long story. I can show you afterwards if you're interested. And of course, they wake up. My God, all this effort that I was writing this paper. Just what does it have anything? And again, this is how you make me feel. Some of you, right? What is this? What am I teaching? So that's, by the way, not a sexy woman, if you understand what it is, right? This is an asshole with eyes. The derivative of e to the x. The derivative of e to the x is e to the x. It's not changed. That's the entire previous chapter on which we spent 2 days. I hope that's clear. Other mistakes are okay. I mean, we haven't covered that. We haven't talked about it, right? Do not just memorize formulas. Try to understand why things work. Because here, let's say what happened. So people that answer this question, and I could have taught you this to be the case. What do you say? You say that the derivative of x squared is 2x, and the derivative of e to the x is e to the x. So most of you wrote 2x times e to the x. Now you do that because, well, I mean, that's a guess, I suppose, right? But that guess is absolutely wrong. If you do not understand why something works, the entire thing is just is going to be meaningless. You understand it? It's not that, oh, so I can tell you a different law, a different property. That's not what I'm trying to teach you guys. I'm trying to teach you to think, and that's very difficult. Okay, and not just about calculus, to think about anything in general, so that you're not just somebody tells you some information and you just spit it back out. So this is absolutely wrong. Every time you encounter anything new, you should right away go to the definition or have some ways of thinking about it. Now, why is it wrong? Let's begin with, I want to introduce 2 approaches. One of them is the geometric approach, okay? So do you remember what it means to be differentiable under a geometric approach? Yes? A geometric approach means that when you zoom in on a curve that's differentiable, you will eventually be seeing a straight line. You will not be able to tell that it's not a straight line. Good? So if I zoom in at some point a comma f of a, what do I see? I see a straight line that will have some slope, which I denote by f prime of a. So this is what I will see. Yes? And there is a good word to learn here. You see, so first of all, guys, x minus a, x is going to be close to a, so I can call it dx. That's for short notation. So it's going to be y minus f of a equal to f prime times dx. So this line is what I call a stunt double. A stunt double, in other words, it represents it's very similar to the actual function locally. And there is a good word that's, it's called in Russian, it's called cascadeur. And it's actually not originally Russian. If you know French, if you know German, that's the same word that they use, probably originally German. But the reason it seems so nice to me because kaska is a helmet, dергать, it's like pulling, right? So it sounds to me like helmet puller when I think of it in Russian, right? And that really represents to me like somebody is going to perform the stunt double. And what is that stunt double is that the function f of x is a prima donna. It's a complicated function. It's hard to use it. But the stunt double, it's a line. And the line is much easier to use than the function. So what we're expecting is that if I zoom in near the point A, then for all x close to the point A, I will essentially see this line. So I may as well use the line for my calculations. And this is the idea. Do you see this curve? This curve is definitely not a line. But if I zoom in at A, in between this red edge and the right edge, it's hard to tell that this black curve is not the red line. Guys, before I continue, are you following me so far? What about the rest of you? Guys, and again, I don't know what you think of. I'm trying to excite you. Any emotion, right? Excite you truly, right? That's the best. So, my God, it's so interesting. It's so amazing. That's the best feeling, right? The next best feeling is, of course, fear, right? I want you I want to use any emotion. If you actually have to survive, that would be the way I would make a class, right? It's like a labyrinth, and if you survive this labyrinth, that means you know calculus. I guarantee, my God, you would be geniuses. Imagine that you have to solve a problem like differentiate x squared times e to the x, and if you don't do it correctly, you're dead. Can you imagine how fast will you know it? You will know it, all of you. My God, cold, like your first language. No, Stephen, right? That's exactly what would happen. You like, my God, right? You would just know calculus. It's survival. So yes. Anyhow. All of those are dreams, right? The school does not have the budget for me to do this for you. So do you understand what I mean? So in this interval, the red line and the black curve, let's say, look to us very similar. Of course, if you zoom in even more, it will be even more so. So I use the red line to calculate instead of the black line, and that can be easier. Let me give you a quick example of how that works, okay? So suppose that I want to calculate root of 9.01. Are you with me, guys? Root of 9.01. Now, what function am I using here? What do you think? What function is used? When I calculate roots, naturally the function that I'm using is well, you can say the function f of x is the square root function, correct? Right, and at some values it's very easy to evaluate. So for example, at 9 it's extremely easy to evaluate, but this number is not 9, it's just close to 9. So what do you think I will do? Hint, hint. What do you think I will be doing? Yes, approximated at 9, but not quite that. What will I do? I will use this linear approximation. In other words, the root function is differentiable, correct, guys? So that I will be zooming near the point here, near the point A, f of A, and I will see a line. And if I write the equation of this line, maybe it will be much easier to use it to calculate. That's called linear approximation. You understand the idea? I'm going to use the line as my stunt double. So let's say with a root, you're stuck, you do not know what to do. But here I can use this number as a stunt double. So here is the procedure. So first of all, let's remember how to take derivatives of root functions. So f of x is root of x. And then the derivative, I can use this definition, right? I decide I can multiply by the conjugate, but I decide to factor the denominator. I can write z minus x as root of z squared minus root of x squared. Same thing, right? Because z is positive since it's a root, right? So that procedure is going to work. Z is going to get close to x, and x has to be not 0 and a positive number for this function to be differentiable. At 0, it's not differentiable. You can see at the end of the formula, right? So I take the limit, and then I'm able to factor the denominator into root of z minus root of x, root of z plus root of x. I can cross the root of z minus root of x. And then I have this limit, 1 over root of z plus root of x. Limit as z goes to x now becomes root of x plus root of x, 1 over 2 root x. That's my derivative. Good? And so what does it mean? It means that if I zoom in particular at the graph root of x at the point 9 root 9, when I zoom in, what will I see? I will see this line, guys. I will see the line y minus root of 9 equal to 1 over 2 root 9 x minus 9. Do you understand? Guys, before I speak fast, I want to cover more material. I'm always thinking, oh, I hope I explained it correctly. Have I explained it well enough? Do you understand me? Do you read my messages? Do you open those notes? You know how upsetting it is if you do not, to me, right? Extremely. I work at this stuff all the time. I work at night, so please do the same thing. I know the material. What's the point here for me? Do you understand that if you zoom in at the curve, you will see this line? Yes? Because what is the equation? What is an equation, to be precise, of a tangent line near 9 root 9? It's the intercept, so it's y minus root 9 equal to the slope. The slope is the derivative at 9, x minus 9, yes? And the derivative at 9 I can easily calculate because it's 1 over 2 root 9. We calculated it for all points. Good? So I know this derivative, and here I even bothered drawing it, you see? You can see how nice it is near 9. You see, this blue interval, it can actually make it wider. You can see that at this scale, there is barely any difference between the red line and the black curve. Good? So then here is what I think. 9.01 is really close. 9.01 is really close to 9. So I'm hoping that if I plug this here, I can instead of plugging it into the root, I can plug it. Here is what I do, right? Instead of plugging it into the root, I plug the value into the line. Yes? And then it's easy to calculate. It's only involving multiplication, right? So it's 3 plus 1 over 6 times 0.01. This is what survives here. And I get an approximation of 3.0016 bar. Yes? And contrast this with the calculation of 9.01. In the calculator, that's the number that will be spilled out. Look at it. You see 3.0016, a bunch of 6 repeated. Look how many digits we actually have. It's a good approximation. You see up to this digit, all correct. Good. That's not a good strategy for approximating roots, by the way. That's not what I taught my several students that left here. There is a very, very simple idea that you can use if you want to calculate roots. Let me quickly show you what it is. So if I had to approximate, for example, root of 2. Think about it. Root of 2 just means a number that when squared gives you 2. So what I do is I look at it. I know what's the biggest integer I have here. It's 1. So it's 1 plus root of 2 minus 1. Have I accomplished anything by that? It's tautology. Nothing accomplished. You agree? No trouble, Zainab. You follow me, guys? Don't lose me, guys. Yes? So you understood the idea. I'm trying to just explain the derivatives stand double, and that's not for the purpose of calculating roots. That's why I'm deviating for a moment, okay? The idea is, you will see in a moment how that is going to be used. It's just, what is differentiability? It means you zoom in at the curve and you are seeing a straight line. You cannot tell that you're not looking at a straight line. So it's called locally linearizable, and that linear approximation that you are seeing is, I call it the stand double or cascadeur, because it is a simpler, a cheaper version of the function that I can use perhaps for whatever purposes I'd like. It locally looks like a line, but that's not what I would use to approximate roots. So root of 2, for example, is not a meaningful thing to me. It just means a number that when squared gives you 2. Remember, if you followed my instruction, as soon as I talked about the exponential e to the x, I was actually able to figure out what it is. Similar for root of 2. That's the idea I would like to talk about in office hours. Look at it. 1 plus root of 2 minus 1. Now look what I can do with that. You know you like completing the square, correct? Or multiplying by the conjugate. So this is 1 plus, I multiply this by root of 2 plus 1. And I obtain 1 over root of 2 plus 1. I obtain this. Also seems useless, but look at it. So this is 1 plus 1 over root, well, I should say this way, of 2 plus root of 2 minus 1. And I have the same pattern now as what I have over here. And so my solution to root of 2 will be 1 plus 1 over 2 plus 1 over 2 plus 1 over 2. And onwards. So let me erase this. I should say this. My solution to root of 2 would be this, guys. Root of 2 equal to 1 plus 1 over 2 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 forever. And is this any use to us? It's extremely useful. Look at it, because what it means is this: I can have this approximation. So one approximation is 1 plus 1/2. Another approximation is 1 plus 1 divided by 2 plus 1/2, which is, if I multiply top and bottom by 2, so that would be 1 plus 2 divided by 5. Okay, and by doing this procedure, if you stay with me after class, I can tell you quite many interesting things and what it really means philosophically as well. Okay, let's go back to the current idea. You understand, guys, what I'm trying to tell you? If you are thinking about something, if you deeply think about it, you really realize so many incredible things. Otherwise, you're just punching in numbers. You're just a boring factory worker. So here, guys, is how that idea of linearization. You see, what I'm saying is stand double. Zoom in, and you will see a line. See if you understand what I'm going to explain now. Here is how I can use that idea to figure out the derivative of the product. Okay, so using geometry. Okay, so I'm assuming that my function f is differentiable at some point a, and that means when I zoom in at the point a, I will see this stand double near f of x, right? F of x is going to look like this line. Before I continue, guys, do you understand what this means? This is the tangent line. This is the equation of the tangent line. It's y minus f of a equal f prime a times x minus a, and I just move the f of a across. So it's y equal f of x. It's the black curve, like in here. Y equals f of x. In general, it's not a line, right? But let's say I zoomed in at 9. The near x for x in this blue region, the red line and the black curve look very much the same. Good. So f of x can be replaced by the stand double, which in short I write as fa plus f prime a times dx. Gx can be replaced by its corresponding stand double, which I write as ga plus g prime a times dx. Now, you understand what I mean by stand double. Whatever, in other words, they look essentially like f and g. So if I multiply them, multiplying f times g, it's like multiplying the two line equations. Do you see that? And then I group them by powers of dx. Dx is just x minus a here, by powers of dx. And what do I see when I group them by powers of dx? I see that the constant term is of the form fa times ga. The term that has one dx is as follows. So it's f prime times g a, and it is g a prime times f a. So and then I group it. So it's basically this times that plus this times that, and then I can factor out the dx. Do you see it? I put it in the brackets. It's just foiling. Nothing else than foiling. And then the quadratic term dx squared will contain f prime g prime. Here it is. Are you following me? You understand what I'm doing, guys? I mentioned all this stuff about stand double. Do you follow? What am I trying to say? What is the stand double idea? Is that instead of using f and instead of using g, I am using their linear approximate. I'm using their cascadeurs, their stand doubles. They are kind of too fancy to be multiplied together or to do this trick. So I'm using the linear approximations. Okay. So the linear approximation is not for estimating roots. That's why I showed you one reason I showed you the root. It's not. I would not have used it for loss estimations. I use it to understand the interrails, the deeper sense, the deeper meaning of those functions. How do they work? What are they about? So if you understand what it is just I'm trying to find again, guys, if fx gx is differentiable and what is the derivative in terms of the derivative of f and g. Yes, that's what I'm trying to accomplish. Now I have this function, and I now ask you. See, this is what I get. Now I'm asking you to be very imaginative. What will I be seeing if I zoom in? Right? Dx is very small. Do you understand? Dx is microscopic. I make dx very small. What line will I be seeing, and why that will be the line? You see, what do? I zoom in on the curve and I try to see a line. And if I see the line, I need to figure out what is the slope of that line. That's the derivative. The derivative is the slope of the line that I zoom at. I hope you remember. I explained that. I tried. What will I be seeing? How many of you are studying biology or medical in the medical field? So you imagine you're looking in the microscope, you're zooming in. All right. Let me help you with that. When I zoom in, that means imagine that I see x within 10 to the minus 6. The units here, let's say, are meters. 10 to the minus 6 meters, it's what scale? It's a micrometer. It's 1 millionth of a meter, guys. Do you know what's a micrometer? It's something that you cannot see with your eyes. You know, if I draw you to points that are within 1 micrometer, you will not see anything. So imagine that I use a microscope that multiplies by a million, by a factor of a million. Right? Imagine it's kind of, I can have a panoramic view, and the micrometer is multiplied by a power of a million. How large will the micrometer appear? Help me. A micrometer, 1 millionth of a meter. I'm using magnifying lenses to make it to make everything appear 1 million times larger. How large will a micrometer look to me? So dx, imagine dx is a micrometer. Yes, and like a meter. Beautiful, Stephen. A micrometer will look like a meter, because what does it mean? This is a millionth of a meter. Multiply it a million times, you get a meter. Yes. Now look at this. You see what I'm talking about? When I'm zooming in, I'm making dx very small. That's what I mean by one of the zoom in part is that the dx, the horizons are just going to be small dx becomes my full screen. Yes, like what are those bars? Do you understand what it means to zoom in here? It means that this will be eventually, if I zoom in at this point, this line here will be my left edge of the screen, and this will be my right edge of the screen. I won't see anything beyond that. That would also be my horizon, right? And if I continue zooming in, then walls that are much narrower around 9 will become my horizons. You following me, guys? Yes. So here you understand how the idea comes around, guys, right? It's not really that you want, again, some of you just plug in a formula. You cannot imagine how I hate that. Do you understand what's happening here? Why have we considered multiplication? Because we want to find the derivative of f times g, and to find the derivative of f times g, we are approximating f by its linear function and approximate g by its linear function. And instead of multiplying f and g, we multiply the linear functions. And that's what we obtain. Dx is the distance of x to a, to the point at which we're zooming. So dx, now imagine that I continue shrinking, and dx now is 10 to the minus 6 of a meter. So it's a micrometer. And then I decide to look at this curve. This is the curve that I look at. I amplify my curve by a millionfold. So dx now appears as a meter. So you look at this appears like as a meter. What does dx squared appear like? Can you see dx squared? Under a millionfold magnification. So when dx is 1 over a millionth of a meter, I zoom in, it now is as large as a meter. It's big. See, the meter is big. Right now, dx squared will be what compared to it? Will I see this factor? Very, very small. So under a million magnification, will I even see this factor? Will I see dx squared factor? That's my question. Do you understand, guys? I'm asking you to imagine. I'm zooming in at this curve. I will see that f looks like a line and g looks like a line. The product of those lines will be what f times g looks like, we would imagine. You understand why? Because f is like this line locally and g is like the other line. And their product is then similar to the product of those equations. They are their stand doubles. They are on a small scale, they are very good approximants to f and g. So their product should be, they should act for f and for g. Do you understand what I'm saying, guys? It's very simple when you think about it. So what does dx squared look like? What does it look like? Can you see it? A dot. Well, yes, a dot. In particular, let's be precise about the scale. If dx looks like a meter under the zoom, dx squared would look like a what? A micrometer. Thank you, Stephen. Do you understand, guys? One person talks to me. I'm not sure about the rest of you. I have 30 something students. Do you understand me? Dx squared. You see, dx squared will look like a micrometer. Please confirm that you understand. If you understand. No, okay. Thank you, Jose, that you said no. I really appreciate that as well. I need to know if you don't get something, please talk to me, guys. Tell me, where did I lose you? Look at it. Do you understand the idea? Would anybody like to talk to me and actually describe the idea to me if they understand it? Would I have such a volunteer? Is it possible that someone in this class will talk? No, I guess not. Not possible. Am I that bad in the morning, a grumpy old man? Come on, talk to me. Who is a brave person? No one? No? Guys, wonderful. Wonderful. Again, F. Now, guys, I can tell you this. I will give you the exam soon enough, right? You don't ask me when, don't worry, you will not miss it. I will see certain questions, right? And I will be, I would want to see that how you understand. There are going to be questions that I will think, did you copy it or did you understand it? And if I begin to think that you copied something, I will get upset. And if I get upset, I will interrogate. Yeah, I'll teach you what is appreciation. And I will, again, I promise you guys that if you do not put the work in this class, I will be rather, a different person, not a pleasant person. Not at all, okay? F of x is a line locally. G is locally a line. That means that f times g is the product of those functions, those linear approximates. What I mean, by the way, yeah, so then the product of f and times g is the product of the lines. It's this thing times this thing, right? So if I then group based on dx, I have no dx, it's f times g, just foiling, right? Then there will be one case of dx. It would be f prime times g plus f times g prime, and then I factor the dx, plus the f prime times g prime times dx squared. Yes? And then in this equation, I'm trying to see where is their line. What is the line here, right? And then I just reason as following. If dx is very small, let's say dx is a micrometer. A micrometer is 1/1,000,000th of a meter. Yes, so then I zoom in under magnification of 1,000,000. Under magnification of 1,000,000, 1 micrometer looks like a meter. So this dx, in other words, it's going to be the length of the interval where I will be seeing this equation, this part of the equation span will be the length of 1 meter. It's huge, right? It's bigger than the piece of paper. But what about this term? Will I be seeing that term on my graph? No, because dx squared will be, see, whatever this thing is, maybe depends of course what's f prime times g prime. It's most likely not going to be a millionth scale, right? It's going to be most likely, it's not going to be a million, more likely, right? If it is, I can make it smaller. You understand? I can always make this so small that it will be invisible. So f prime times g prime times dx squared will be invisible under that zoom. As when this is 1 meter, this is a micrometer, so this is invisible. So I'm going to see this line. You see, the equations tell you what you will see if you can understand scale, that this part will just not be noticeable at all. So under the scale, most likely, of course, it depends, of course, on the coefficient, they can make it large, right? It's not just dx squared, it's the coefficients, but usually they're not the size of a meter, they're not usually huge. They have to be really huge to be noticeable for this expression to be noticeable. Yes? So under the scale of 10 to the minus 6, most likely you will only see this part if you zoom in 1 million times. Make the scale even smaller, you can zoom in more, and this will still be invisible. Okay, so you're zooming in and you're seeing this equation of the line. Okay, this is dx squared, it's 10 to the minus 6 squared, which is equal to 10 to the minus 12. Now, guys, the thing that I mentioned again, right, because I'm seething at it, right? I see no faces except for one person. And I just hope you understand this, right? That, you know, if I see that, say that you cheated on the exam, or I suspect it, and you're not appearing on the screen, you're not talking to me, you're not turning it on, I will just simply deduct the 30 points, and you can then decide to prove, in other words, guilty until proven innocent. I do not like that you do not study enough. I do not like that you do not participate. I do not like it. This is what it all means. So this is the y coordinate, this is the slope. This is what I'm seeing. So that's my derivative. Good, so here is the same thing done by definition. I can just, again, take the derivative of f times g, and we get this limit. This limit, then I have to recognize what am I searching for in this expression. I am searching for f of z minus f of x over z minus x, and for g of z minus g of x over z minus x, because those, I assume I know their derivatives. I can calculate. Here is then what's missing. Numerator. I can what I need is I need somehow to factor out gz gx, right? So in the numerator I put minus fx gz plus fx gz, because then I can break it apart. I can break it apart left and right. I can factor out here, for example, I can factor out gz. Here I can factor out fx from this part. Yes, I just break it apart like this. This here and this here. Yes, so that's what you see here. I am able to factor out. I'm able to factor out here this part, and here I'm able to factor out this part. So it's just object recognition. I see that I can put it in this form. Yes, it's this plus this. So then I figure out what is this limit. So this limit here is f prime. This limit here is g prime x. And then limit as z goes to x of g of z equals to g of x. It's very easy to miss this one part. Why is that true? Why is the limit as z goes to x of g of z equals to g of x? Z is becoming x, Steven, but it's not enough. It's very suggestive, but you might miss something. What do I know about the function g? The function g, when I calculate this limit, we're assuming it's differentiable. You understand that you don't necessarily replace you don't necessarily plug in the value when you take limits. Remember, that's not what's happening usually, right? It's just when the function is what? G has to be what for this to be true? You are right, Stephen, that Z is becoming X, but that's in the limit. It's not the same. Remember, in the limit, you do not plug this value. You're plugging approximants of X. Why will G react to approximants of X in the same way it reacts to X? Again, by hypothesis, G is differentiable. So by hypothesis, this limit, the derivative limit exists. Do you remember? If a function is differentiable, it is what? Continuous. Differentiable function is continuous because zoom in at the function, it looks locally like a line. Do you remember that? So if differentiability implies continuity, that's what we mentioned. Do you remember the thief? So this is the derivative formula. F prime times G plus F times G prime. And this formula is very easy to remember. The derivative just travels from first function to the next through addition. Now calculate the derivative of x squared times e to the x, please, and write in the comments. Yes, see if you can calculate this derivative. You see, this is now the formula that we obtained. I hope you understood how we obtained it. The derivative of f times g plus f g prime. You understand? So when I have two functions that I recognize, here you have x squared and e to the x. Each of them you know how to take derivative of. What happens is that the derivative, look at it, starts at first function, doesn't touch the second function, plus moves to the second function. Do you see that? Easy to remember this formula. So what do we get? Yes, Christian, you can do it this way, or I prefer to start with the left function, yes? So Kirill, yes. And what about the rest of you guys? Come on. Do I scare you? I hope I do scare you at least a little bit to do the work. I was taught beautiful stories about horrible math teachers. You know, every German person had a horrible math teacher, apparently, right? Definitely everyone I speak with. It was cruel. Okay, 2x, e to the x, x squared, e to the x. Lisa, sorry. Good. What about the, so do you understand, guys, how I did it? Okay, here is, you learn this shortcut and you do it very fast, but please, I beseech you, I implore you, learn the material, right? Like I want to see, my God, good quality, you know. good quality meat coming out of the university. X squared e to the x. Derivative of f is 2x, g is intact, plus f. Derivative of x squared is, we don't touch it. Here, derivative of e to the x is e to the x. Do you see how I did it? So it's 2x e to the x plus x squared e to the x. We still have so few functions that we can calculate. Let's do the next problem, guys, right? And let's be very careful about it. The derivative of x to the power of 1 over n. So how do I take derivatives of roots? Let's say x to the power of 1 over 5. What was the derivative? X to the power of 1 over 7. What's the derivative? Write in the comments, and perhaps, I mean, that's kind of difficult to communicate without sharing the board. Perhaps you can tell me how you know. You can tell me how you know what's the value of this derivative. Do you understand what I asked, guys? What's the derivative of x to the, in other words, in general, what is the derivative of something like x to the 1/2? We did it x to the maybe 1/5. Yes, that's what I'm asking. What's the derivatives of those expressions? That's correct. But do you know why, guys? Can you see that you remember? That's wonderful. But you see, or if you can kind of guess what, but I always want you to figure out why it's true. So we can do it by either geometry or definition. I kind of did it by definition. You want to, we'll see it by geometry later on. Okay. So here is how I think to solve such problems. So by definition, it's z to the 1 over n minus x to the 1 over n divided by z minus x. And what I can do is I can write the denominator as z to the 1 over n to the power of n minus x to the 1 over n to the power of n. And then I have factorization of n powers. You see, I just imagine this is just v and this is u. I factor it. I simplify what's crossed out, and I'm left with this, right? So I'm left with, when I push in the limit, I have 1 over x to the 1 over n and minus 1 plus blah, 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 x to the 1 over n and minus 1. So I get 1 over n x to the, how many copies? We have, each of them is n copies, x to the n minus 1 over n, which is, I can write like this. It's 1 over n, 1 over x to the 1 minus 1 over n. And then I can flip the power and write it as 1 over n x to the 1 over n minus 1. As you said, right? So I can very quickly figure out and explain why something is the case. It is the why that matters. Now, this memorizing it is meaningless, guys. Do observe it. So then I can have, I can verify using the derivative that, let's say, x to the 1/3 times x squared is 1/3 x to the 1/3 minus 1 times x squared plus x to the 1/3 times 2x. I can use this. I can use product rule here. Yes? Now, could you quickly find the derivative of c, guys? Find the derivative for c. The functions that are awkward, but that's one thing, is we only know e to the x and we know polynomials. So there's not many things we know, maybe roots. That's right, ping ping for b. So yes, guys, solve. You see, you can see that part of c is b, right? B is part of c. So in general, I would like to hear the answer to c, but you can start with b if you prefer. And I'll tell you maybe another thing, another shortcut. So for b, one thing is for b, one thing is x to the 1/3 times x squared. You might have noticed that it's the same as x to the power of 1/3 plus 2. Yes, 1/3 plus 2. Now it's actually, what do you think is the derivative of x to the 1/3 plus 2? It ends up being, you drop the power, so it's the power rule actually ends up working. 1/3 plus 2 times x to the power of 1/3 plus 1. The thing is, we have not verified that the power rule works for numbers other than integers. So for example, when we actually derived it, we know that if it's x to the 5, and then I take the derivative, it's 5x to the 4. And we just did in part A, we again verified that if it's x to the 1/5, then the derivative is 1/5 x to the 1/5 minus 1. Okay, we verified it for such fractions, but 1/3 plus 2 is already a different number. So once we are in chain rule, we can verify that pretty simply. You can think about other ways to do it. You can, if you prefer, unless I say otherwise, you can use this idea. In other words, if I say calculate, just calculate the derivative, I will note on the exam take points and say if it's x to the power of any alpha, where alpha is any real number, the derivative ends up being alpha x to the alpha minus 1. That ends up being true all the time. But we have not verified it ends up being true all the time. We only verified it to be true for integers and for 1 over an integer, if you noticed. You agree? And so you should be cautious in general. Whenever you do not know something, then maybe you are wrong. It actually ends up being even true for complex numbers. If I take, let's say, x to the power of root of -1, and I take the derivative, that will be root of -1 x to the power of root -1 minus 1. This power rule always works for constant powers. So, okay, what's the derivative for C? Very simply, we already here we observed what's the derivative for x to the 1/3 times x squared. It's product. I did it here by product rule because I wanted to be consistent, right? I cannot just use the power rule where I haven't proved it. So I wrote it, simplified it. It's 1/3 plus 2 x to the 1/3 plus 1. So the derivative here, this part is simply 1/3 plus 2 x to the 1/3 plus 1. And the derivative of the second part is another product rule. So it's plus and then another product rule, which is 10 x to the 4 e to the x plus 2 x to the 5 e to the x. Are you following, guys? This is just, again, there's really, here, it's just the procedure. Do you need more explanations about it? If f, g, and k are differentiable, what do you think is the derivative of the product f times g times k in terms of the component functions? You understand what I'm asking? So imagine that you can calculate the derivative of this function alone, this function alone, this function alone. What do you think will be the derivative for the product? Write in the comments. Of a triple product. It's one function times another times a third. How would the derivative look like? Well, I don't mean the graph of it, but I'm saying what formula do we have for the derivative? F, G, K, how would that, in other words, imagine that I have something like this. X squared e to the x and maybe the root of x. Right, so and I don't want to combine root and x squared, because, so how does the derivative of this triple thing looks like in terms of the derivative of x squared, e to the x, and root of x? F, g, and k is the general situation. Yes, beautiful. Beautiful, Khalil. You would have the traveling derivative. So the pattern is rather simple, right? Here I suppress the x to write it easily. F times g times k, the derivative begins at first, f. Everything is untouched, plus the derivative moves to g. And then plus the derivative moves to k. That's the pattern. And it's very easy to verify if you know the product rule for two functions, because the derivative of f times g times k is like the derivative of the function f times g times k. And that means the derivative of f times g times k plus f times g times k prime. And then the derivative of f times g is just f prime g plus f g prime times k plus f g k prime. And when I simplify it's basically, it gets us to be f prime g k plus f g prime k plus f g k prime. Okay. Now, derivative of product rules to higher order. So I don't have to just have product rule and I take one derivative. One derivative looks like this, guys. Let's see how good you are at picking up patterns. The derivative of f times g is f prime g plus f g prime. Now let's try to take the derivative twice. That's f prime g plus f g prime, and then there is a prime, right? And then it's addition. So, and then we have f double prime g plus f prime g prime, right? I just take the derivative of this expression, that's one prime at this first guy, the second intact, plus this intact times g prime. So this part is here. This part is here. And when I combine, it's f double prime g plus 2 f prime g prime plus f g double prime. Does it look like something familiar? Look at this expression. Does it remind you of something? Let's see what happens if we take triple prime. Triple prime, it means I have, this is the expression of doing double prime. And then take one more prime. And when you carry out the calculation, this is what you get. Now, before I move on, does it look familiar to you? Does it look like this formula, it reminds you of something else? Yes, we're doing yes, it's very much so, right? First of all, we're trying to understand what it means to take more derivatives. Again, there are a few examples that are interesting that I can give you because we know very few functions, right? Once we have quotient rule and other things, we can introduce more things. So this looks like the expansion of degree 2. Look at it. Look at it. One derivative x plus y. Right, it's derivative is at x, the derivative, it's to the power of 1. It's like first thing, second thing. Look at when I square. First thing squared, 2 times first thing not squared, second thing not squared, and second thing squared. Look at it. Do you see what I'm saying? The double prime is like the square, right? The prime is acting like the power here. Notice that the primes, the dashes add up to 2. Binomial expansion, exactly. Do you see, guys? The differentiation looks like binomial expansion. Look at that. So higher order derivatives function like binomial expansion. To show that symbolically, note that, well, I'm going to write a derivative of f like this and derivative of g like this. Okay. So then we have derivative f plus derivative g times f times fg. It's just the derivative of f times g plus the derivative of g of this expression. So it's this what we have. You understand that this is the symbolics, guys? I'm just using, this is partial f, partial g to indicate just take the derivative of f, just take the derivative of g. Yes? So the expansion, in other words, do derivatives twice. That would be derivative of f plus derivative of g squared, which will be derivative of f squared to derivative f derivative g plus derivative g squared. Okay, let's see if you, before I continue doing it, can you very quickly calculate the second derivative of x squared e to the x. Okay, I want you to calculate not one derivative, but actually 2. See if you can do it fast. You can see my whiteboard, yes? Okay, let's see, guys, what it is. The idea is this, okay? So here is the function f, here is the function g, good? So what should I have? I should have the two derivatives of f times g, binomial expansion, yes? Plus 2 f prime g prime plus f plus f g double prime. What is f double prime? So derivative of x squared twice. It's 2x, and then it's just 2, right? Derivative of x squared is 2x. Derivative again is 2. So this is 2ex plus 4x ex plus x squared ex. Good? Let's do one more before you leave. I'll keep it simple. Two derivatives, let's have it as maybe 5 plus x minus x cubed. And again, for lack of imagination, e to the x. Find the second derivative of that, please, and then goodbye. If guys, you really have to go at some time, you have another class or something, I don't hold it against you. But hopefully you will stay and solve this problem before you finish this lesson. And I have little hope, but I do hope that some will remain after class and we talk about what I mentioned about the roots and about some other ideas. If you let me, I can teach you quite a lot of things. If not, what can I do? You can keep an inventory of what you're doing there, guys. So say that This is f. This is g. We know what's the derivative of f. The derivative of f is simply 1 minus 3x squared. And I will need, of course, two derivatives of f. That would be minus 6x. Okay, so let's finish this derivative quickly. Okay. So then what's the derivative, guys? So I need to take two derivatives of f, that's over here, and multiply by g. So that's minus 6x e to the x plus 2 multiplied by one derivative of f times one derivative of g. Derivative of g, they're the same. So it's really 1 minus 3x squared e to the x. Finally, it's plus the original function, which is 5 plus x minus x squared and e to the x. That completes this problem. Okay, so yes, I will stop the recording. If anybody would like to remain, we can talk about either the problems you're solving to prepare for this material. We can talk about this root thing. So many interesting things, truly. And the root thing has to do with a philosophical idea. I actually remembered it in light of a discussion, in light of the Chinese room. Do you know the Chinese room problem, guys? It's a philosophical position against strong AI. And then I thought about the root thing as an example of something.